Can you guys hear me? All right, so let's get started. I'm Jakub. We will be presenting our geometry-aware trained encoding. In this work, we have been looking at the problem of how to encode input into a neural network, specifically how to encode the position in 3D space for a neural network like an MLP, for, let's say, algorithm like a neural radiance caching. And I understand that not everybody is working with neural networks all the time, so I will do a little introduction to the problem that we are trying to solve. Let's start by thinking about why some kind of encoding is even needed. Let's say we have this little problem, like we have points in 2D space specified by 2 coordinates, and we want to train our neural network to classify them between red points and green points. So we can just put these 2 coordinates as input to the neural network as 2 neurons. It's not a very difficult problem. Even a small neural network will be able to learn it quite fast, but with a suitable encoding or mapping or transformation of these 2 inputs, we can make a job for the neural network much easier. So in this case, let's imagine there is some center point in the middle of these red points, and we apply a transformation to these 2 coordinates. We introduce a 3rd coordinate, which is a distance from the center, and we will plot it on the chart on the right. And now we will see that actually classifying these points into 2 groups is absolutely trivial. You don't even need an MLP to do this. It's just a comparison based on this decision surface. This is commonly called the kernel trick, although the real kernel trick is much more involved. But I think it's a very good example why transformation, even a very cheap one, can make the neural solution much more efficient. So let's take it closer to the practical solutions. So previously, each of you could stare at the problem for a minute and figure out the best possible transformation to do it. Well, in practice, that's not so easy, and finding a good encoding function might be very tedious. It might be impossible. Such function might not even exist. So people started to use what's referred to as learnable parameters or trainable parameters. The way this works is, let's first define our encoding function as a mapping from our input space to some higher dimensional other space that can be a variable, and we implement it as a lookup table. And entries in this lookup table, they're essentially defining our mapping, and we can train it together with the network, specifically using the backpropagation. If you look at the diagram over here, you can see we have some lookup table, which is actually a grid, and then you get your input parameters, and then you put it to MLP. So the way backpropagation works, it propagates the error back through the network to your lookup table, and you can actually train it together. So automatically, you will get some mapping, which is optimal. It's not guaranteed to be the best possible, but it will work. What I found the best about this is that you can change your network, you can change your problem, and you don't need to think about encoding functions because they're automatically trained. So in this specific example, this image is borrowed from neural texture block compression. So as I said, the basic idea is to store these trained feature vectors in some grid or a lookup table. They give you mapping to higher dimensional domain, and you can also have multiple of these tables with different resolutions, different settings. For example, on this image, we have 2 grids. One is smaller, one is higher. You just encode your input point using both. You concatenate the resulting vectors, and you use that as an input to the MLP. So let's now get to what is the state of the art in this currently. I believe it's the multi-resolution hash encoding introduced a few years ago. We just call it hashgrid for short. And it's exactly what I described on the previous slide. It's like you have a grid overlaid your input domain. You can have multiple resolutions of these grids. What the hash grid adds is a hashing, so to reduce storage and also possibly increase the efficiency and quality. Instead of storing all the feature vectors, you map them into a hash table. So what are the problems of these implementations? One is that you get interpolation artifacts. Of course, the grids are discretized, and let's say you want to encode a triangle in a 3D grid. Basically, every time you query your grid for every triangle, you get some interpolated result from nearest vertices of the grid. So it's never trained properly for your specific point in space. With the hashing, you also get hashing artifacts due to hash conflicts. If you use it for neural radiance caching, for example, these exhibit as weird colors, weird blobs, black blobs, or blurriness where you don't expect it. A pretty big problem is that you get scattered memory accesses because the grid is hashed. For 3D space, you need to load 8 vertices from completely different memory locations due to hashing. So you get perfect incoherency in your cache accesses. And the last problem is that the input domain is limited. Being a finite grid, you need to put it somewhere, usually stretch it to the whole scene using a scene bounding box. But what do you do when you do not have a bounding box on open-ended worlds or these games which just stream the geometry in and out? Scene box can change all the time, so this is a problem. And of course, if you're not querying your network in empty space, you are wasting storage to represent empty space which you're not using. So finally, let's get to our solution, which is very, very simple idea. So instead of storing these feature vectors in a grid, let's just store them directly on the geometry, on the surfaces. So I will talk on the next slide how we distribute those feature vectors using mesh colors. For now, let's look at what advantages can this idea give us. So suddenly, the cache incoherency is gone because we don't use hashing. We have cache-friendly query, assuming your meshes are optimized for cache coherency. You can follow the same layout as you use for your index buffer, and you get nice cache-friendly accesses. There are no hash collisions, and interpolation only happens on the surface of your triangle, not within a volume of a grid. This is a big advantage because maybe for the hash grid you will have multiple triangles within the same cell, and then suddenly the hash grid needs to be trained for maybe completely different triangles. This cannot happen with our solution. We do not need a bounding box because you have your geometry. You can decide where to put your feature vectors, maybe all of your geometry or maybe just a part of it. And this essentially also deals with the teapot in the stadium problem. Let's say you have a huge scene, but you only render small parts somewhere. With the hash grid, you would have to do some tweaking, magic, bounding box skewing to make it work. With our solution, you just have your feature vectors where your geometry is. Thanks to all what I said, we get higher performance. I will get back to this. And now, disadvantages, of course, you need more storage, possibly a lot more storage. It depends on how much geometry you have. And it's only limited to surfaces, so you cannot query it in empty space. Maybe you have some algorithm which can be used in empty space, like some shadows, light sampling, these things. With our solution, that is not possible. And finally, we can only encode 3D positions, like I said, over triangles. Those hash grids, they can be used in 1D, 2D, 3D, maybe 4D if you do some magic. Ours is just 3D positions on triangles. So let's give you a little teaser of what results we get. So on top we have the example of neural ambient occlusion. So very simple, we just train neural network to do AO. And with the hash grid, which is stretched over this relatively large scene, you get a lot of blurriness in this case. And with our gate approach, we essentially get a very good solution. Like I said, this is solving the teapot in the stadium problem. Now on the bottom image, we have a neural radiance cache. I have to tell you, this is queried on the primary vertex to show you what it looks like. That's not how NRC should be used. You will do a few bounces of light, and then you will query the cache. But that will give us noisy results, which are hard to read. I just find this much easier to mentally parse the image like what you see. So some imperfections are expected. I'd like to point out these tiles on the back wall with the violet light. So even in the small scene like this, where you don't have the teapot in the stadium problem, the hash grid cannot represent those tiles on the wall. They just basically completely disappear, including the violet light, which should be on them, while our solution works with these two. So let's now talk about how we store these feature vectors. We use a mesh colors algorithm from Jakub and friends. If you're not familiar with it, it's very elegant, simple idea. We just want to distribute more samples over the surfaces of triangles and over the edges. And these can be shared, so the encoding is seamless over edges. It is controlled by a parameter called the resolution. We have image of 3 different resolutions. So the second smallest one is just adding 1 sample per edge, and then higher ones also add some on the surface. It's a very elegant algorithm. All you need to do is to decide what resolution you want to use for your triangle or the whole mesh, and you query it by triangle ID plus barycentrics. The algorithm gives you indices of those samples and their interpolation weights. So very simple algorithm. The code is actually simpler than the hash grid. And you can hierarchically stack these. It's the same as with the hash grid, where you have multiple resolutions. You can do this with ours as well. In our tests, we have used 2 resolutions. One was per vertex, so R equal to 1. And then we had adaptive resolution. So we figured out pretty quickly that using 1 resolution for the whole scene doesn't work. You can see this on the left. It takes 75 megabytes, and it's not very well distributed. We want to use roughly the same size, these little patches. So we have a simple solution which figures out your resolution per instance. Not only we achieve kind of equal-sized patches of mesh colors, we have also managed to reduce memory consumption with this. So why don't we go one step further and have per triangle mesh color resolution? Just quickly mention that it's difficult because then you have a mismatched number of samples over shared edges, and you have to do some magic to interpolate them correctly. We didn't want to go through this for this paper, but it can be done, of course. Now let's talk about how we train this. As I said, the idea is super simple. Instead of the grid stored on the geometry, but it enables us to do some very nice things. We have used Adam Optimizer to train our network. And so my next point is only train updated feature vectors. So first I have to tell you how the hash grid implementation we used worked. So the hash grid in typical setting has like 1 million entries. So you can actually execute the dispatch call to work on each entry with a single thread, and you apply Adam Optimizer on each entry of a hash grid. The original paper even suggests you can skip training the entry if gradient is 0. They get some 10% increase in performance, I think. Well, technically for Adam, you should never do that because the point of Adam is the momentum. So when the gradient is 0, it can be stuck in a local minimum, and Adam is designed to get it out. So even if the gradient is 0, you should apply the training. So with our solution, we can do this perfectly. We only run Adam on triangles that have been actually trained, which were assigned a training sample. And it's actually must for our implementation because we cannot run a dispatch call big enough to cover all of the feature vectors over all of the geometry. That would be too much. So we have a site buffer where we store where have been the training samples assigned, and we only train those. And that enables us to do what we call per triangle learning rate. So if you know how Adam works, it has some parameters called beta, which are updated after every training iteration based on number of training iteration applied to the vector you are trying to train. And with the hash grid, you have to use global number of training steps, but you're not training all the grid cells all the time. But with our solution, you can track actually how many times was each triangle trained, and you can apply this properly. So we achieve continuous training with momentum using Adam for each vector. So how do we generate the training data? With the solution I described so far, you can do some nice things here as well. So when you know how many times has each triangle been already trained, you can use this to do importance sampling and generate training data on undertrained triangles with preference. So the way we do this is, let's say we're generating some screen space samples, just deciding where to put our training data in screen space by sampling the G-buffer. We can, for each pixel or each training example, we can pick 16 candidates, read how many times they have been trained, and run some importance sampling loop to select one with higher preference. And you can do the same for world space samples. You just sample the index buffer, pick some triangles, and do the same. Now, with generating training examples in world space, I didn't get super great results with that, because if you think about just this scene, there would be training examples generated behind the cupboard, basically in unreachable areas of the scene. So I think this could be some good idea for future work, just detect which areas are not reachable and you don't need to train them. And these images actually demonstrate difference between using importance sampling or not. So if you notice in the red circle on the top, there are some very tiny triangles in the creases between the tiles on the wall, and they are undertrained after 32 iterations, and it exhibits as some kind of glow. And with our fix, using same 32 iterations, it's much, much better. It's still visible, but it's converging much more quickly. So let's get to the results. We have used this for 2 different algorithms, neural ambient occlusion, super simple thing. We have used the feature vector of length 2. So that's our input encoding does the encoding from 3D space to 2D space, so it's not actually embedding to higher dimensional space, but lower. For NRC, we found we need to have more features per feature vector, so the length is 8. As I said, we only query it on primary hits. And an important difference between our original implementation of NRC and ours is that for the hash grid, the original implementation uses a lot more inputs. There's a scatter direction, normal, roughness, and some reflectances. And I believe in my mind, it's designed to kind of help neural network identify which surface you're querying, because as I said, every voxel in this hash grid can be straddled by many triangles. So this is additional information that helps the NRC algorithm with hash grid do better. But it complicates the problem, right? And for gate, we do not need to do that, because each feature vector is bound to every triangle. So we use less inputs for gates, and we actually get better results with these less inputs. Because when we add these inputs, it's shown on the left, we get some color fringes, simply because the problem is more difficult to train, to learn. And as I said, we use 2 stacked resolutions. That's less than for the hash grid. For the hash grid, we use 8 resolutions. With gate, we can only do 2. That's another point where our performance increase comes from, and we still get the better quality. So this is a few results on the neural ambient occlusion of hash grid versus gate. The best result we get for the Vespa in Bistro, which is the teapot in the stadium problem, which was kind of what we designed for. But we do get lower flip error for every scene, even the small ones. Now let's look at the radiance caching, a more difficult problem. It's basically very similar results, but I'll point out to the last row where we do get worse flip error with our gate. Just slightly, but it's there. But I would point out to you, again, those tiles with the violet light, they're missing from the hash grid. So even if the flip error is almost the same, there are missing features that cannot be measured with flip, I guess. So in terms of performance, we have done several comparisons. You don't need to read the whole table. I think the most relevant for practice is comparison of the first row, which is gate hours, and the last row, which is hash grid small. It's not apples to apples comparison because hash grid is using much, much less memory, but it's how I would use it in production. So I guess that's fair comparison. If you want to look at equal memory comparison, it's the first two rows, hash grid large and hours. But those are hugely in favor for us. The training performance is very, very slow for the hash grid. And it's because we use that implementation which executes the compute dispatch over all of the entries. So, but the bottom line is that we still get about 1.7 to 2.7 faster inference with our solution. It's because we have coherent memory accesses, simpler code, and we have simpler network with possibly with less inputs. Like I said, flip metrics is always better for gate, except for that one example, even regardless of the hash grid size. So let's talk about training speed. And here I don't mean training speed as in the clocks or time, but in terms of training iterations. You can see that after 16 iterations, our gate is already looking pretty good, while the hash grid is still learning. But the most important thing on this image is the chart. The orange line is the hash grid, and you can see that it plateaus pretty quickly, and then it just becomes horizontal. It doesn't get better with more training, while our solution gets progressively better because it's adapting to the geometry of this scene. So we're almost done. Let's now take a look at some videos. First videos, a neural radiance cache in Bistro for the primary vertex. And this has not been pre-trained. This is trained in runtime as I started the application from frame 0. You can notice how it trains on the disocclusions. Now it will do a turn, and you will see some training in runtime. I should have told you that I also removed the color, the textures, so that we can see this better. So next video is the same thing, but in comparison to the hash grid. It's side by side. So hash grid flickers somehow. And of course, this is a bad example for the hash grid because it's this teapot in the stadium problem. I have another video later which is more fair in terms of scene size. Okay, so next video is ambient occlusion in interior. I will tell you that the camera will fly around and then it will cross the door. It will enter the train. And that demonstrates how our per triangle learning rate actually works, because then it suddenly sees stuff it has not seen before. It sees it for the first time, and because of this per triangle learning rate, the learning rate will be very high for these newly seen triangles, and it will adapt very quickly. So let's see that. 3, 2, 1. Yep. And once more, again, the same thing, comparison to hash grid. Okay, and the last video is the neural radiance cache again on a very small scene where actually both approaches are using equally same memory as out of the box without any tweaking. I want to show you this specular highlight on the floor. The camera will move around and the specular highlight will follow. So I want to demonstrate that our method works dynamically for dynamic scenes, even the specular highlights. But I needed to increase the learning rate to double the usual amount, so it will flicker elsewhere. So let's just see it. So again, far from perfect, but works. And there's some flicker on this wall behind. So see it once more with the hash grid. Okay. And since this is kind of neural paper where ablation studies are standard, which I like, let's very briefly talk about stuff that didn't work. I said that lowest resolution we use is per vertex. We have tried to go one resolution lower to go per triangle, but that revealed discontinuities between triangles. So it was not worth it. Mesh colors without edge sharing, again, discontinuities, that's useless. You have to go through pain to implement that. Using only single mesh color resolution, that was very bad for training. And learning the interpolation, this is the idea borrowed from the neural texture compression paper, where we would not interpolate these 3 nearest feature vectors. We will just throw them into MLP, concatenate it, and we would hope that MLP would learn to interpolate these vectors in the best way. Well, turns out the best way is the linear interpolation almost always, and it just takes ages to learn, so that didn't work. So the summary, we achieve better performance. We can do nice things like per triangle learning rate and adaptive training data generation. We have simpler MLP because the less inputs. We remove the problem of normalization of input to the scene bounds, but we do require a lot more storage, and we are limited to 3D positions on the geometry. So for the future work, we want to do what we call the clustering. For very finely tessellated geometry, even the per vertex feature vectors are too much, so we want to do per cluster. Don't know how yet, but it needs to be done. We want to do some adaptive mesh colors allocation to the scene. I think it would be nice to say we have a fixed budget of 100 megs for this, just distribute my feature vectors in the scene where they will be useful. I don't want to do this myself, but maybe someone can try a different mesh parameterization, like a PTEX. I like mesh colors. Some people hate them, so go figure it out how to do it without them, I guess. And we want to do pre-training. We can think of the MLP as a decoder for some fixed representation that would solve a few problems you can read on in the paper. So I thank you for your attention. And let's hear your questions. Thank you.
Yeah, so we are behind the schedule, so just 2 questions.
Hi, thanks, nice talk. You were mentioning the teapot in the stadium problem multiple times, and this problem comes with two sides. Like, you have a large scene, but you're only focusing, and everything which is important to your image is only like one small thing, like you zoom in on the teapot, meaning that everything else around the scene is more or less not important for you. So, and usually the problem with these fixed resolution grids is, yes, you have a huge grids, meaning you have large cells. But the other side is, if you make a high resolution grid, you just waste a lot of memory. And now it seems you went from the one side to the other, because if your solution is now to tessellate the scene and make all these small MLPs at each cell, then you probably waste a lot of memory for stuff you will never touch, and it's not impossible. I think you mentioned it a little bit in the end with the adaptive coloring.
Yeah.
So have you thought about some sort of adaptive tessellation and then distribute it afterwards?
Yeah, so this is all future work, and you are absolutely right that we just, for many scenes, we cannot allocate for all the geometry, and you have to somehow figure out which parts are needed. So yeah, that is just the future work. The biggest limitation of this, what I presented now, so yeah.
Because for hash grid, you would probably try something like cascaded hash grids, which overlay and...
Yeah, or you can just repeat the hash grid, just hash it to the same locations. That's also possible. You can do it.
Okay, thanks.
Any more?
That's gone. Really good work. Very
Thank
good
you.
presentation. Very interesting. You touched on a few things, like magnification and dealing with high vertex density, and magnification, and when you interpolate between values and so on, right? And looks like some of these problems are also the problems that Nanite, for example,
Nanite, yes.
tackles, right? So I was curious, have you tested on anything like Nanite, where you have clusters and more unified geometry density?
No, but this kitchen scene is a little bit like Nanite style, where you have many tiny triangles on the wall. It takes 75 megabytes if you do single mesh color resolution for the whole scene. And then when you just assign lowest resolution just for these triangles, the memory consumption goes down to 20 megabytes, so 4 times almost. And the quality actually goes up, because if you have these tiny triangles still tessellated more, you are only training one tiny little patch of sub-pixel size. That needs to be solved. That's like the biggest problem, what I see with our method right now.
Thank you.
Okay, the last comment is please return to your best paper below to this box. Yeah. And let's thank the speaker again.
Thank you.